Hello everybody, this is Dr. Ritu Singh from Basic Science Department, and today's topic of discussion, actually there are two topics. One is graphite, the other is liquid crystals. So I am going to start with graphite. So the first topic of discussion is graphite. As we all know, it is an allotrope of carbon or polymorph of carbon. So two important polymorph or allotrope of carbon are graphite and diamond. If we compare the two, then graphite is more useful and is more stable in comparison to diamond. So graphite, it is an allotrope of carbon. We have two allotropes of carbon. Out of two, graphite is more important, and the reason is it is more stable. Now if we come to the structure of graphite, then this is the structure. It has got layered structure. This is one layer, then this is the second layer, the hexagonal arrangement can be drawn as you wish. This is the third layer of graphite. Now the carbons are hexagonally arranged, so this is the presence of carbon atoms. So here in graphite, the carbon is having a hexagonal arrangement. So this is the arrangement of or the structure of graphite. So graphite, basically it is having a two-dimensional structure, or it is a 2D structure. It is having a planar structure. So graphite has got a 2D planar structure. The carbon which is present is sp2 hybridized. So the carbon is sp2 hybridized, and because it is sp2 hybridized, so one valency of carbon is free, and because of this, graphite can act, or it acts as a good conductor of electricity. Then if we see the arrangement of carbon, it is having a hexagonal arrangement. So carbons are hexagonally arranged, plus we can see it is present in layered. So hexagon arrangement, and it has got layered structure. Now graphite is having two types of bonding. It is having covalent bonding, and it is having a van der Waals force of attraction. So within the layers, suppose this is the layer, within the layer the bonding is covalent, and the order is 1.4 angstrom. So this is the order of covalent bond which is present in the graphite. So within the layer, the bonding between the two carbons is covalent bonding, and the order is 1.4 angstrom. And between the layers, bonding is explained in this manner. This is between the layers. The bonding between the layers is van der Waals force of attraction. So between the two layers, the bonding is van der Waals. The order of van der Waals force of attraction is 3.4 angstrom. So this is the basic structure of graphite. So graphite is having a 2D planar structure. It is a two-dimensional planar structure. The carbon which is present is sp2 hybridized. It has got layered structure, and within the layer, or the arrangement of carbon is hexagonal. Within the layer, the bonding is covalent, and the order of the covalent bonding is 1.4 angstrom. Between the layers, the bonding is van der Waals force of attraction, and the order is 3.4 angstrom. Now if we consider the two type of bonding, which is van der Waals and covalent bonding is more stronger. So because of the presence of this covalent bonding, the structure of graphite is having a firm structure. So the structure of graphite is firm. Why? Because between the within the layers the bonding is covalent, and because of this firm structure the melting point of graphite is very high, 3700 degree Celsius. So this is the melting point of graphite, which makes it chemically inert but is very useful. So because of the presence of covalent bonding within the layer, it provides a firm structure to graphite, and because of the presence of this covalent bonding the melting point of graphite is very high, which is 3700 degree Celsius. That is why graphite is very useful in furnace, like in metallurgies. So this is because of the presence of covalent bonding. Now if we come to the second type of bonding, which is van der Waals force of attraction, because of van der Waals force of attraction is a weaker force. So if we provide energy to this structure, what happens is these van der Waals forces, they are going to weaken or they are broken, and because of this the layers, they can slide over each other. So this layer can slide over this layer, or this layer can slide over this layer. So as we provide heat, the van der Waals force of attraction is going to break, and the layers can slide over each other, and because of this the layers when the layers are sliding over each other, it is soapy in touch. So the structure is soapy in touch, and that is why the graphite can be used as a lubricant. So we have two types of bonding, covalent and van der Waals. So if we summarize the structure of graphite, it is a 2D planar structure. The carbon is sp2 hybridized within the layer. It has got a layered structure. Within the layer the bonding is covalent. The order is 1.4 angstrom. Because of the presence of covalent bonding, it provides a firm structure to the graphite, and because of this the consequence of covalent bonding is the melting point of graphite is very high. It is of the order of 3700 degree Celsius. Now between the two layers the bonding is van der Waals force. It is a weaker force. So if we provide some energy to this structure, this van der Waals force of attraction is going to break, and the layers can slide over each other, and because of this, because of the presence of van der Waals force, or because of this phenomena, it is soapy in touch and can be used as a lubricant. So this is about the structure of graphite. Then we come to types of graphite. So basically we are having two types of graphite. One is alpha graphite, second is beta graphite. Now alpha graphite is a natural graphite or naturally occurring, whereas beta is synthetic. Now the basic difference, one difference is this, that it is natural, this is synthetic. Now in case of alpha or natural graphite, the arrangement of carbons is hexagonal, as we have already seen in this structure. So it is having hexagonal arrangement of carbon. Whereas in case of beta graphite or synthetic graphite, the arrangement is rhombohedral arrangement of carbon. So we have two types of graphite, alpha or beta, or we can also say that we have two types of graphite, natural and synthetic. In case of natural, the arrangement of carbon is hexagonal. In case of synthetic, the arrangement of carbon is rhombohedral. Now further, this alpha graphite or natural graphite is divided into three parts. Three types. One is crystalline graphite, the second is flake, and third is amorphous. So the difference between crystalline and amorphous is, here we have regular arrangement of constituent particles, but in case of crystalline graphite, the arrangement of constituent particles is regular, whereas in case of amorphous structures, the arrangement of particle is not regular. But when we come to graphite, here amorphous doesn't mean that the arrangement is not regular, or we are not going to consider that. So we are going to talk in terms of crystal structure only. So here the constant particles have got a regular arrangement. It is a perfectly crystalline structure like solids, and this crystalline graphite is obtained from crude oil. So in nature, the crude oil deposits which have experienced or which have gone through a large change in temperature and pressure with time is converted into crystalline graphite. So if we talk about the origin of crystalline graphite, it is obtained from crude oil deposits which are present in the nature. Then if we come to amorphous graphite, here the graphitic carbon is very less. So but we are concerned only about the graphitic carbon. And what does graphitic carbon means? Where the arrangement is as we have discussed in the structure. So here the amount of graphitic carbon is less, whereas if we talk in terms of graphitic carbon, then in crystalline the graphitic carbon is high, the percentage of graphitic carbon is high. Now if we talk about flake, flake is in between crystalline and amorphous graphite, and flake graphite is obtained from metamorphic rocks. So this is the origin of flake graphite, natural graphite or alpha graphite. So these are the three types of graphites: synthetic graphite, which is crystalline, flake and amorphous. Here it has got it is having large amount of graphitic carbon. Here the amount of graphitic carbon is less, and in flake we can say that the graphitic carbon is between, the amount of graphitic carbon is between crystalline and amorphous. Now if we talk about flake, it is obtained from metamorphic rocks. Then if we come to synthetic graphite, which is beta graphite, the arrangement, as we have already I have already said, it is rhombohedral. The example is graphene. This is the example of beta graphite. So this is the classification of graphite. Then we talk about the applications of graphite. So in the syllabus we have got number of short notes. This is one of them. So whenever you are asked to write down a short note on any topic, you have to write down application, because the subject if we talk in terms of subject, then we are studying applied subjects. We are not you are not going to study pure chemistry. So you have to study applied chemistry. So applications are must. So the first application and the important application of graphite is it is used as refractory material. Now refractory material is a material which is used in furnace, where the temperature is around in thousands. So it can be 2000, it can be 3000 and so on. So refractory material is a material which can withstand high temperature. Now why it is used as a refractory material? Because within the layers the bonding which is present in graphite is covalent, and because of this it is having a firm structure, and the melting point is very high, which is 3700 degree Celsius. So graphite can be used in furnace. Therefore, it is a refractory material. So if we have to say in one line that why graphite is used as a refractory material, it is used as a refractory material because it is a chemically stable substance. Chemically stable. Why it is chemically stable? Because the temperature, the melting point is high, which is 3700 degree Celsius. So this is one of the applications of graphite. The second application is it is used in batteries. In battery we use crystalline graphite. Then it can be used as an anode. This is another important application of graphite, that it is used as an anode. Then it has got electrical applications. in electrical applications, for example, the carbon brushes which are used in electrical motors, they are made up of graphite. So that is the electrical application of graphite. Then we have mechanical application. If we talk about mechanical applications, then it is used in bearings and carbon based seals. So that is the mechanical applications. It is used in bearings, and it is used in seals, which is carbon based seals. Then the other applications are it is used as moderators. It is used as moderators in nuclear reactors. So what happens in nuclear reactor is we are having fast moving neutrons. So to slow down the speed of neutrons, we use graphite, so which is used as a moderator. So it is another important use of graphite. It is used in as moderators in nuclear reactors. Then a very important use is lead pencils. So graphite is used in writing in lead pencils. Then it has got an application it is used in air purification devices. So they are used in the air purification devices. And then the important use of this graphite is used as a lubricant. So basically it is used as a solid lubricant. Why it is used as a lubricant? Because it has got layered structure. Between the layers we have got van der Waals force of attraction, and when we provide heat, the van der Waals force of attraction breaks, and because of this the graphite is soapy in touch. So because it is soapy in touch, it can be used as a lubricant. So this is another application. So about applications, it is used as a refractory material, it has got electrical application, it has got mechanical applications, it is used in batteries, it is used in amorphous, it is used in batteries, it is used as anode, then it is used as moderators, it is used in lead pencils, air purification devices, and lubricant. It has got one more important use. It is used in aerospace. And in aerospace, the graphite which is used is synthetic graphite. So these are all applications of graphite, and it is a basic, it forms a basis of what is nanotechnology, as we are going to discuss in next lecture. So this is all about graphite. So if I summarize the whole of graphite, then graphite is an allotrope of carbon. Basically we have two allotropes of carbon, one is diamond, the other is graphite, but graphite is more important and more stable in comparison to diamond. And one more important thing about graphite is it forms a link between metals and non-metals. And then when we come to the structure, it has got a 2D planar structure. The carbon is sp2 hybridized. It has got layered structure. Within the layers the bonding is covalent, and between the layers the bonding is van der Waals force of attraction. Because within the layers the bonding is covalent, so it gives a firm structure to graphite, and as a consequence the melting point of graphite is very high. It is 3700 degree Celsius, and that is why it is used as a refractory material. Then between the layers, because the bonding is van der Waals force of attraction and the order is 3.4 angstrom. So if we heat or we provide stress to the graphite, or we heat graphite, if we provide heat treatment or thermal treatment to graphite, what happens is van der Waals force of attraction is going to break and the layers can slide over each other, because of which it becomes soapy in touch, and because of that it is used as a lubricant. So we have two types of graphite, a natural or synthetic, or alpha or beta. In natural, the basic difference is natural is having hexagonal arrangement of carbon, and the synthetic is having rhombohedral arrangement of carbon. Then we have got three types of natural graphites, which is crystalline, flake and amorphous. And then we come to applications. Regarding application, it is used as a refractory material, it is used in batteries, it is used as an anode, and then it is used as in aerospace, and it is having electrical application, it has got mechanical application, it is used in lead pencils, it is used as a lubricant, and it is used as in air purification device. So this is all about graphite. Now we come to the second topic of today's lecture, which is liquid crystal. Now, if we all know that we have got three states: solid, liquid and gaseous state or vapor state. We have one more, which is plasma, but we are not going to discuss here. So basically we have got three states: solid, liquid and vapors. But regarding liquid crystals, we have got certain substance which form an intermediate state between solids and liquids. So they are known as liquid crystals because like crystals or like solid, they have got a crystal structure, but they can flow like liquids. So if we have to explain it on the basis of an equilibrium, then this is the equilibrium. Solids, they form a crystal state, and then this crystal state or liquid crystal is going to form a true liquid. Now, this solid is converted into a liquid at a temperature which is a transition temperature. And this liquid crystal is converted into liquid at melting point. So transition temperature is a temperature where one solid is converted into another solid. So liquid crystal, this is how we can represent the liquid state. So liquid state is intermediate state between solid and liquids. Not all the solids, they behave as liquid crystal. We have got certain substance or solids which are going to behave as a liquid crystal. So why the name liquid crystal? Because like crystals, like solids, they are having a crystalline arrangement, but they can flow like liquids. So because this state is intermediate between solid and liquid, it is also known as mesomorphic state. Mesomorphic state means in between solids and liquids. Now, not all the substances are going to behave as liquid crystals. We have got certain substance. The examples are cellulose or cellulose derivatives. They behave as liquid crystals. Paraffins, cholesterol esters, they behave as liquid crystal. Glycol compounds, they behave as liquid crystals. So we have got certain substances which are showing this behavior. Now why this behavior is there is, suppose if the compound contains azo group, if it has azo-oxy group, or it is having carbon-carbon double bond, or the compound is having carbon-carbon triple bond, and with these compounds it is having a long chain of hydrocarbon, that compound is going to behave as a liquid crystal. So if I have to write in general, then the structure of liquid crystal is this, or it is just an example, not actually the structure. This is Y and this is Y. So Y here is a long chain of hydrocarbon, and X is the group I have mentioned. It can be an azo group, it can be as an azo-oxy group, it can be a compound having carbon-carbon double bond or carbon-carbon triple bond. So if this is the structure, then that particular substance is going to behave as a liquid crystal, which is a mesomorphic state. It is a mesomorphic state, that means it is a state between solids and liquid, and that is known as liquid crystal. Now what makes a substance behave as a liquid crystal, and what is the importance? So if we consider the structure of solid, this is the solid. It is having a layered structure and particles have got a definite arrangement. Now if we make an arrangement of liquid, This is the liquid structure. The force of attraction here is strong. They have got a constant particles are having a definite arrangement, but here the force of attraction is weak and the particles, the force of attraction here is weak and the constant arrangement, there is no definite constant arrangement of particles. Now, if we come to liquid crystal, this will be the state. So, like solids, it is having a crystal structure, but it is not so much intact as it is present in case of solids. So, because the structure, the force of attraction is not so strong in comparison to as compared to solids. So, this is the liquid crystal state. So, what happens here is in liquid crystal state, in some of the part of the solid, the force of attraction is very strong, but in the other part the force of attraction is weak. Suppose if this is a crystal, a substance which is going to behave as a liquid crystal. Now, in this portion the force of attraction is strong, whereas here the force of attraction is weak. So, what happens is if we provide energy to such a substance, the portion where the force of attraction is strong, that will remain intact and will behave as a solid. But the portion where the force of attraction is weak, they are overcome, and from this portion will start behaving as a liquid. From this portion it is going to flow. So, that is the structure of liquid crystal. It is between solids and liquids. So, if we have to describe the structure of liquid crystal, it is having two parts, a rigid part and a flexible part. Rigid part is also known as mesogen, where the force of attraction is strong. A flexible part is responsible for fluidity of the liquid crystal. So, this is about liquid crystal, the structure of liquid crystals. And we have next we come to classification of liquid crystals. So, if we talk in terms of classification of liquid crystals, then basically we have two types of liquid crystals. One is thermotropic liquid crystal, and the other is lyotropic liquid crystal. So, the basic difference, I am going to first start with thermotropic, and after completing I am going to come to lyotropic. So, basically if we study classification of liquid crystal, there are of two types of liquid crystal, thermotropic and lyotropic. So, I start with thermotropic liquid crystal. So, in case of thermotropic liquid crystals, as the name suggests, some of the substance, they start behaving as liquid crystal as we change the temperature, but the range of temperature is fixed. So, within the range, if we are changing temperature, the substance starts behaving as a liquid crystal. If the temperature is too high, then it is going to behave as liquid, and if the temperature is too low, it is going to behave as solid. But within certain range of temperature, certain substance, they start behaving as liquid crystal as we are changing the temperature. So, those substances are known as thermotropic liquid crystal. Then we have different type of thermotropic liquid crystal. So, the first is isotropic. So, next we have types of thermotropic liquid crystal. The first is isotropic liquid crystals, thermotropic liquid crystal. So, if we arrange here, these are the molecules. Now, one more thing, in liquid crystals we have got two types of molecules, the shape of the molecule. One is this rod shape, the other is in the form of a disc. So, this is oblong and rod shape, and this is in the form of disc. So, liquid crystals, the shape is two, one is rod shape, the other is in the form of disc. So initially I am going to draw in rod shape. So isotropic liquid crystal, this is the arrangement of molecules. So as we can say, in most of the time it is not even considered as a liquid crystal, and if we see the structure is same as that of pure liquid. There is no difference. For example, if we take up the water, the properties of water, or the chemical or physical properties followed by water, is followed by isotropic liquid crystal, with only one difference. If we apply electric and magnetic field to pure liquid, it shows no alignment. But if we apply electric or magnetic field to isotropic liquid crystal, it is going to show alignment that can be seen in the optical properties. If the liquid crystal is clear, it will become opaque, and if it is opaque, it will become clear. So this is one type of isotropic liquid crystal, and I should say once again, it is in many books and many times it is not even included as a liquid crystal. Then the second is nematic liquid crystal, and this is the arrangement of molecules here. So it looks like a bunch of molecules. Now if we talk about solids, we have got two types of orders. One is positional order, the other is orientational order. Positional order means the constituent particles, they are present, if they are present at the lattice site as they are present in solids, then we say that the solid is having positional order. Orientation means head on one side and tail on the other side. Suppose if this is the structure, then this is the arrangement, and if this is the arrangement, the molecule is having orientational order, and if this arrangement is this way, this molecule is not having orientational order. So if we talk in terms of solids, if we take pure solids, it has got positional order as well as orientational order. Now when we come to nematic liquid crystal, it is having orientational order. That means head on one side and tail on the other side, but it is not having positional order. As we can say, this see, this molecule starts from here, ends up here. Here it starts here, ends up here. Here it is starting here and ending here. So no position of molecule is there. So if we see the structure of nematic liquid crystal, it is a polarizable rod-like structure. It is having orientational order, but it is not having positional order, and it is the simplest liquid crystal which is known. So this is nematic. If we come to the third one, this is sematic liquid crystal. In case of sematic liquid crystal, this is the arrangement of molecules. I am going to draw only two layers. So if we compare these two structures, here there is orientational order, but there is no positional order. Here for the first time, in case of sematic liquid crystals, the molecules are present in layered structure. So, and they are having orientational order. So with orientational order, they are having some sort of positional order also. So if we compare these two, this is more organized in comparison to nematic liquid crystal. And one thing more, sematic liquid crystals occur at a lower temperature in comparison to nematic. Now we have got number of sematic liquid crystals, but the important ones are A and C. So if this is a plane, a normal of the plane, this is sematic A and this is sematic C. So as we can see with the in the structures, in case of sematic A, the molecules are arranged parallel to this normal, but in case of sematic C, the molecules are not parallel, but they are present at some arbitrary angle. So angle can change, but they are present at some angle. This is sematic liquid crystal. So in case of sematic liquid crystal, if we say sematic liquid crystal occurs at lower temperature in comparison to nematic, the molecules are more organized, because now the molecules are appearing in the form of layers. So it is having orientational order, but it is also having positional, some sort of positional order. We have got number of somatic liquid crystals, but the important one are A and C. The basic difference between the two is in case of A, the molecules are parallel to this normal, whereas in case of somatic C, they are present at some angle. And the fourth type of liquid crystal is cholestric. Cholestric liquid crystal. Now, in case of cholestric liquid crystal, one thing important is the molecule should have or the substance which is behaving as a liquid crystal should have a chiral carbon. So, we know what is a chiral carbon, where the 4 groups attached are different. So, this is the condition for the molecule to behave as a cholestric liquid crystal. The molecule should have a chiral carbon. Now, the structure of cholestric liquid crystal is similar to nematic as well as somatic. Like somatic, it is having a layered structure. So, this is how we are going to represent the layers. So, these are different layers. So, like somatic liquid crystal, it is having layered structure. Now, within the layers, the arrangement is like nematic liquid crystal. So, to show it here, the molecules are arranged vertically, then in the second layer they are placed horizontally, then they are placed at some angle. This is the angle. In the next one, the angle is going to change, and then again the arrangement is changing. So, this is the arrangement of cholestric liquid crystal. So, the structure is in between somatic and nematic. Like somatic, it is having layered structure, but within the layer, the arrangement is like nematic liquid crystal. And in different layers, we are having different arrangement of molecules. This shows that one layer is twisted with respect to other layer, which is very important, and it can be seen by this structure. The arrangement of atoms or the arrangement of molecules in each layer is different. So, this is cholestric liquid crystal. The next type of liquid crystal which we are having is columnar. Columnar liquid crystal. Now, in case of the basic difference between the other type of liquid crystals and columnar liquid crystals is, in all the type of liquid crystals, whether it is isotropic, it is nematic, it is somatic, or it is cholestric, the molecules are in the form of polarizable rod-like structure. But in case of columnar, the molecules are present in the form of disc. That is the basic difference. So, and the arrangement of disc can vary. It can be present vertically, it is present hexagonally, but the arrangement or the shape of the molecules is in the form of a disc. So, these are different type of thermotropic liquid crystal. So, the first one I discussed is isotropic, then we have nematic, third is somatic, then fourth is cholestric, and finally the fifth one is columnar liquid crystal. So, if we see the difference, isotropic, most of the time it is not even considered as a liquid crystal, it is just like water, pure liquid. The only difference is when we apply electric or magnetic field, it is going to show alignment, and that can be seen in the optical properties. In all the liquid crystals, if we apply electric or magnetic field, they are going to show alignment. So, that is a basic property. Then in case of nematic, they are polarizable rod-like structures, and they have got orientational order, but they are not having positional order. In case of somatic, for the first time the molecules are present in the form of layers. They are having orientational order, but some sort of positional order is also present. In case of cholestric liquid crystal, the structure is between nematic and somatic. Like somatic, they have got layered structure. Within the layer, the arrangement is like nematic liquid crystal, and one layer is twisted with respect to other layer. And the last is columnar. In case of columnar, the difference between other liquid crystal and columnar is, in columnar, the liquid crystals or the substance are present in the form of disc. So these are the type of thermotropic liquid crystal. Now we come to the second type of liquid crystal, which is lyotropic. Lyotropic liquid crystal. It is amphiphilic in nature. Amphiphilic means it is having a polar part and it is having a non-polar part within the molecule. For example, if this is the structure, head is polar and the tail is non-polar. So within the molecule, it is having a lyophobic part or it is having a lyophilic part. Now the substance which behaves as a lyotropic liquid crystals are, we are having certain substance which below a particular concentration, they behave as true solutions. And this concentration is known as CMC, which is critical micelle concentration. Now above this concentration, these two solutions, they form aggregate of molecules and that is known as micelle. This is the structure of micelle. Head part and tail part, and it has got an orientational order. Head is arranged in one part and tail on the other part. So certain substance below a particular concentration, which is critical micelle concentration, they are going to behave as a true solution. But above that critical micelle concentration, they form aggregates, an aggregate of molecule which is known as micelle. Now what happens is, as we increase the temperature or as we decrease the temperature, depending upon the nature of the substance, the size of the micelle, it keeps on increasing. It reaches a saturation point, and after reaching a saturation point, if we are going to increase or decrease the temperature, this micelle is going to burst. And the point or the temperature at which it is going to burst, there we say that the lyotropic liquid crystal is formed. So micelle, on increasing or decreasing the temperature, the size is going to increase depending upon the what type of substance is there. It reaches a saturation point, and after which it is going to burst out as lyotropic liquid crystal. Now thermotropic liquid crystals, they are having technical applications, whereas lyotropic liquid crystal is having biological applications. The upper portion of the skin which we are having is made up of lyotropic liquid crystals. The heavy food which we are taking, like meat or vitamins or proteins, they are first converted into lyotropic liquid crystal and then they are taken up by the blood or they are assimilated into our body. So heavy food is not directly taken up by the body, it is first converted into lyotropic liquid crystal and then it is taken up by the blood. So lyotropic liquid crystal is having biological applications, whereas thermotropic liquid crystal is having technical application. So this is about the classification of liquid crystal, and at the last we have applications. So regarding applications, it is used in large displays. For example, liquid crystals, they are used in TVs, they are used in computers, then they are used in small displays. Third, they are used in portable displays. Portable displays like PDAs and mobiles. So we use liquid crystals. Then it is used in sensors. In sensors, we can check stress and temperature. As we change the temperature, the color of the liquid crystal is going to change. So every change in temperature, the color is changing. So we can sense the temperature changes. Therefore, it is used in sensors, and same is true with the stress. Then it is used in office screens. So private office screens which are used, we use liquid crystals. Then the other uses of liquid crystals are, it is used in gas liquid chromatography. it is used in gas liquid chromatography because the properties of liquid crystals are in between solids and liquids. So, and they have got better electrical and mechanical properties. So, therefore they are used in gas liquid chromatography. Then it is used to find out the structure of anisotropic substance or anisotropic molecules. So it helps us to find out the structure of anisotropic molecules. So these are some of the points or applications of liquid crystal. Liquid crystal, one more is there, it can be used as a lubricant also, commercial lubricant. So these are applications of liquid crystal. So if I summarize the whole, liquid crystal, it is a substance which is, or it is a state in between solids and liquids. Like solids, they have got a crystal structure, but they can flow like liquid. And why it is happening is, in some portion the force of attraction is strong, and in the other portion the force of attraction is weak. So if we provide stress or we provide energy, what happens are the portion where the force of attraction is weak, that is overcome, but the portion where the force of attraction is strong, it remains intact. So in that portion it is going to behave as solids, and the portion where the force of attraction have been overcome, there it is going to behave as liquid. So it is a mesomorphic state between solids and liquids. Not all the substances they behave as liquid crystals. I have already taken up the examples, and a particular groups which should be present in those substances. So for a substance to behave as a liquid crystal, it should have an azo group, it should have an azo-oxy group, and it should be a long chain of hydrocarbons. Then we have got two types of liquid crystals, thermotropic and lyotropic. Thermotropic is having technical applications, and we have different type of thermotropic liquid crystals are isotropic, nematic, sematic, cholestric and columnar. And lyotropic liquid crystals, they are formed from substance which above a particular concentration they behave as micelle. So as the size of the micelle increases, after reaching a saturation point, they burst out as lyotropic liquid crystal, and lyotropic liquid crystal is having biological applications. And then we have got applications of liquid crystal. There is one more application, is it is used in to estimate tumors inside the body. So the cholestric liquid crystal helps to detect the tumor which is present inside the human body. So these are the applications. It is used in large displays, small displays, portable displays. It is used in sensors, it is used in screens, then it is used in gas liquid chromatography. It helps us to find out the structure of anisotropic molecules. It can be used as a solid lubricant, and last, it helps us to detect the tumor inside the body. And for tumor detection, the liquid crystal which is used is cholestric liquid crystal. So this is all in graphite and fullerene. Thank you.